have 311 joules. Something like that.
6.3 times 10 to the third joules. So that's how much energy is in the gas. And then if the gas is contained in a volume of that, what's its pressure? Now this one, you can just go back. You could go back to that pressure formula. It might be fun if you want to use the pressure formula. But I haven't given you what kind of gas it is, so you don't know the molar mass of it.
Right.
So you need to go back to the ideal gas law and go back to the nRT. So the volume then, pressure is what I want. Pressure is equal to nRT over V. And I'll let you solve that. That's just plugging in. There you go. And when you do that, you'll discover you get 1.40 times 100 Pascal. Pressure. Okay, then the last one before we move on is tank contains 135 moles of argon, monatomic argon gas at a temperature of 15.3. How much energy must be added to increase its temperature to 45 degrees Celsius? So this is heat we're going to add. Okay, so we know the energy is equal to 3/2 nRT. So the change in energy is going to be equal to the amount of heat we add, Q. So that's going to be equal to energy final minus energy initial, but that's going to be 3/2 nRT final minus 3/2 nRT initial. So it's just 3/2 nR times the delta T. So I know how many moles. 3/2, 135 moles. R is 8.31 joules per Kelvin mole. But what's delta T?
It is 29.7.
Right. Did you have to change it into Kelvin?
Can if you want to, but
Can if you want, but you could subtract the two Celsius temperatures as well, because the Celsius degree is the same size as the Kelvin degree. You get the same number. Oh, let me check that before I write it up in there. Well, so you said it was yeah, 45 minus 15 should come out with 5. Is that what people came out with when they did this? You put the 29 in there?
well, no, I didn't.
What did you come up with? Did I do that wrong?
No, I mean, no, I didn't put the.
You didn't put it in there?
Yeah, that's about right.
Well, anyway, chugging through those numbers. And you should come out with 5. At least that's what I did. 5.0 times 10 to the 4th joules. So notice here what you've got is by adding heat, you change the temperature. Well, you've seen that before, right? When you talked about specific heat. You saw that specific heat is equal to the mass times the specific heat times the change in temperature. So the amount of heat you added to a substance times the mass of the substance times the specific heat will give you a temperature change. When we deal with gases, though, we usually talk about them in terms of molar specific heats, because rather than using mole to measure, or mass to measure the amount, we use mole to measure the amount. And so if we look at this kind of situation, where we're adding heat to a gas, and this platform is pinned, so it can't move, so the volume of this gas never changes. Then if we look at this as a pressure versus volume graph, then we're going from this pressure and volume up to a new pressure and volume and up to a new point on a different isotherm, because the temperatures increase. So we just change the pressure without changing the volume. Okay? So what we just saw in that last problem is that Q, the heat added, now I'm going to rewrite this, but in terms of moles. So it's the number of moles times the specific molar specific heat, which we represent by a capital C. This molar specific heat is done at constant volume. So the volume does not change. So this is the molar specific heat at constant volume, and the temperature change. But what we found out from the last problem is this Q is equal to 3/2 nR times the change in temperature. This is for a monatomic gas, for a monatomic ideal gas. That argon we used was a monatomic ideal gas. So just looking at these two equations, then you can see for a monatomic ideal gas, because this cancels out and this cancels out, that the molar specific heat is 3/2 of R. So we know what the molar specific heat is for an ideal monatomic gas. But now let's change the experiment a little bit. Let's take the pins out of that platform so that it can rise up. Well, now when we add the heat, in addition to the temperature changing, so we go from one isotherm to another, the volume changes. So now we have a volume change, so now we have P times a change in volume. We can find an area on the pressure and volume graph, so this means that we've done work. Because once we have area on the pressure volume graph, that means some work has been done. So the heat, in addition to changing the temperature, has done work. Well, let's go back and write the first law of thermodynamics and see what that means. So we know the work done is equal to the pressure times the change in volume. But from the ideal gas law, we know that's also equal to nR times the change in temperature. Notice the pressure didn't change here. This was done at constant pressure because this weight setting on top of here didn't change. So the force of the platform didn't change. So the ideal gas law requires that this quantity, the change in volume, be equal to nR times the change in temperature. Now then, if I write the first law of thermodynamics, that says that the change in energy has to equal Q minus the work. Okay? But I know that the work is equal to nRT. Now, Q in this case is going to be equal to the number of moles times the molar specific heat, but this time done at constant pressure, times delta T minus nRT. And the energy, again, is going to be 3/2 nR delta T. So now I can solve this. All the nR's go out. Not the R's don't, the n delta T's go out. And then if I pull this over here, I'm left with 3/2 R plus R equals Cp. So in this case, Cp is equal to 5/2 R. Or another way to write that is that the molar heat at constant pressure is equal to the molar heat at constant volume plus R. This is 3/2 plus R gives you 5/2. So this is a general relationship. The molar heat at constant pressure is equal to the molar heat at constant volume plus R. Now what this leads us to is something called the equipartition of energy theorem. What this says is that every kind of molecule has certain degrees of freedom, which are independent ways for the molecules to store energy. And this is what I was alluding to earlier. Each degree of freedom is associated with it, on average, 1 degree, or energy of 1/2 kT per molecule per degree of freedom. So if I have a monatomic molecule like helium, I only have 3 degrees of freedom, because it can only move in the X, Y, and Z axis. It has 3 translational degrees of freedom, no rotational, so it has a total of 3 degrees of freedom, so CV is 3/2 R and CP is 5/2 R. And that's where you get the KT is 3/2 R, and the 3/2 in the energy equation. But if I go to a diatomic molecule like O2, then I can rotate around this axis and I can rotate around that axis. Rotating around this axis, it has very little energy because there's a very small moment of inertia around that axis. So I have, for this molecule, I have 3 degrees of translational plus 2 degrees of rotational, so I have 5 degrees of freedom. Each degree of freedom adds a 1/2 kT, so that gives me 5/2 R for the CV and 7/2 R for CP here. So, since the energy in general is CV delta T, for a monatomic, it's 3/2 R. For a diatomic, it's 5/2 R. For a polyatomic, then I've got 3 degrees of rotation because that other axis comes into place, so I get 6. So I get 3R and 4R here. And this doesn't tell the full story, because if I get up to higher energies, I can also excite the oscillating modes. Quantum mechanics tells us that all these modes aren't excited at every energy. At the very lowest energies, the translational modes are excited. Even at very low temperatures and low energies, things can move, but they don't necessarily rotate. You have to have a little more energy before you start exciting the rotational modes, and you have to have even more energy than that to start things oscillating. But once you get high enough, you can have energy stored in motion, translational motion, rotation, and oscillation, so those specific heats go up even higher. So it takes more energy to raise the temperature because you have more places where you can store the energy. So that's what this idea of degrees of freedom. And the interesting thing about it is energy is equally partitioned among the modes. Each mode, each degree of freedom gets 1/2 kT of energy. All right, now let's go talk about these thermal processes. There are 4 basic thermal processes. distinguishes them is the thing in the process that doesn't change. So the first one is a process where temperature doesn't change. That's an isothermal process. So a process in which the temperature of an ideal gas or another working substance remains constant is called an isothermal process. So in an isothermal process, the gas moves down a line of constant temperature on the pressure versus volume graph, and this is called an isotherm. So these curved lines are isotherms. When you saw those curved lines on your lab, those are the curved lines that you graphed when you moved the pressure and volume, changed the pressure and volume in your syringe, keeping the temperature constant. So you formed an isotherm on a pressure-volume graph. Now, what we want to know here is, so if the pressure and volume change in the process, if the final volume is greater than the initial volume, then the process is called an isothermic expansion. If it's the other way, then it's called an isothermic compression. Now, what we want to know is, what is the work done by an ideal gas? Well, the work done is just going to be the area under the curve in the pressure-volume graph. So, what we know is that the work is equal to the pressure times the change in volume, PdV, right? So to get that area under the curve, we basically want to integrate this from the volume initial to the volume final, PdV. But we need to express this as a function of volume in order to do this integral. But it's an ideal gas. So since it's an ideal gas, we know that PV equals nRT. So P is equal to nRT over volume. So I can plug that in there. So that gives me the integral from V initial to V final of nRT dV over V. This is an isothermal expansion. So N is constant, R is constant, and T is constant. Isothermal, T is constant, right? So I can pull them all out of the integral, because they're all constant. So that gives me nRT times the integral from VI to V final, dV over V. Anybody know what that integral is? Natural log of V. So it's nRT, natural log of V, evaluated from VI to V final. Well, that becomes the natural log of V final minus the natural log of V1, V initial, right? And how can I write the natural log of V final minus the natural log of V1? So, the work done in an isothermal process is nRT, the natural log of V final, over V1, or V initial. That's the work done. How much is the energy changed in an isothermal process? Ah, think carefully about that. What's energy proportional to? From all we've talked about before, what's energy proportional to?
Temperature.
Temperature. And in an isothermal process, does the temperature change? So if the temperature doesn't change, can the internal energy change?
No. Evidently no.
No. So since there's no change in temperature of the gas, there's no change in internal energy. Delta E internal is 0. So if I write the first law of thermodynamics delta E internal equals Q minus W. I now know what W is. This is 0. In an isothermal process, all the heat that goes into the system or out of the system goes into doing work. None of it goes into changing the internal energy of the gas. So since this is 0, that means that the heat equals the work. So Q equals nRT, natural log of V final over V initial. So in an isothermal process, the change in internal energy equals 0 because the temperature of the gas doesn't change. And from the first law of thermodynamics, the heat equals the work equals nRT, natural log. So that's the characteristics of an internal, or of an isothermal process. Now let's look at a different kind of process where something different stays constant. This is an isobaric.
Constant pressure.
Constant pressure, correct. So with constant pressure, this is what it looks like on a pressure volume graph. The pressure stays constant. So now we cross from one isotherm to another, so the temperature does change. So that means the internal energy does change in here. So work is done. And so on an isobaric process, we know that the amount of work that's done is just equal to the pressure, which is constant now, times the change in volume. And if you remember, for an ideal monatomic gas, the change in energy is equal to 3/2 nR delta T, which is 3/2 times n CV, or excuse me, n, the 3/2 goes with the CV, is n CV delta T. Now, if you don't have a monatomic gas, don't put 3/2 here. If you have a diatomic, put 5/2. If you have a polyatomic, put 3/2. So now you don't have to stick with monatomic anymore. If you go with CV here rather than 3/2 R. So now you know that's the delta E. So now from the first law of thermodynamics, you can then write that E equals that, the delta E internal equals that. Okay, so now you've got N CV delta T equals Q minus P delta V. But if it's an ideal gas, then this becomes nR delta T. So now you've got N CV delta T plus nR delta T equals Q. So now you've got CV plus R times N delta T equals Q, and CV plus R is CP. CP.
You said P delta V equals nR delta V.
P delta V equals nR delta T from the ideal gas law.
Okay, because it looks like you divided by nR delta V.
There. I'm substituting. So, for isobaric processes, the work is equal to P delta V, the change in internal energy is N times CV delta T, and the Q is NCP delta T. So that gets us isothermal, that gets us isobaric. The last one, and then I want to do a problem, and then we'll But the last one is the most basic of all. That's the isochoric process, where isochoric means the volume doesn't change, constant volume. So I'm changing temperature again. So I'm crossing from one isotherm to another, but I'm doing it at constant volume, so the pressure changes. How much work is done? Zero, because there's no area under the pressure volume graph. So in an isochoric process, no work is done. Okay, so then by the first law of thermodynamics, delta E internal equals Q minus W. If this is 0, then Q equals delta E internal. But for an ideal gas, we've just shown that delta E internal is equal to NCV delta T. So, and this really shouldn't be shocking. For an isobaric process, which is done at constant pressure, Q is equal to N times the specific heat at constant pressure times the change in temperature. For an isochoric process, which is done at constant volume, Q equals N times the specific heat at constant volume times delta T. All makes sense. And the change in energy is always equal to N times the specific heat at constant volume times delta T. So I want to just go through the one of your worksheet activities, or a couple of your worksheet activities, just to make sure we've got the flow of these processes, and then we'll end up with the last process, the adiabatic process, and that will get us through everything. But let's just go through the flow of both the isothermal process and the adiabatic and the isobaric process. The isochoric is so basic, you know, we'll just leave it. So here's the isothermal. Okay, so we've got a sample of 10 moles of monatomic ideal gas held at a constant temperature, so that tells you it's isothermal, expanded from that to that. So what's the initial pressure of the gas before the expansion? Okay, for that you can use the ideal gas. So before the expansion, P initial is going to be equal to nRT times the initial volume. So plug that in. You know the number of moles, so you've got 10.0 moles. 8.31, I'm not going to write the units because I'm tired. 1000 K over the initial volume, which is 0.1 meters cubed. Okay. Chug that through the calculator.
8.31 times 10 to the 5th.
8.31 times 10 to the 5th. Good. What's the initial energy of the gas? Okay, well for that, we use energy equals, it's monatomic, so I can use 3/2 nRT. So that's going to be 3/2 times 10 moles times 8.31 times 1,000 kelvin. So that's its starting energy. Plug that in, type. You're about as fast as I am walking over here, so you got it yet?
Nope.
No? Okay. I'm not, no pressure.
Oh, 124,650.
125 times 10 to the 5th joules. All right, so that's the initial energy. Now it gets a little more complicated. How much work was performed during the expansion? Well, if you remember, the work done by an isothermal is nRT times the natural log. So this one will be a little more challenging to do quickly. The natural log of, it's the final divided by the initial. So it's the natural log of the final, so this is an expansion, so it's 0.2 Well, it won't be that, meters cubed over 0.1 meters cubed, so it's gonna be the natural log of 2. So you plug in to your calculator natural log of 2, then multiply the natural log of 2 by 10, 8.31, and 1,000 times the natural log of 2 will give you the amount of work.
5.8 times 10 to the fourth.
8 times 10 to the fourth, see if that's right. 5.76, yeah, times 10 to the fourth. So that's the amount of work. And this work was done, since this was an expansion, the work was done by the gas. So the work was done by the system. What's the final energy state of the gas? This one you don't even have to calculate, because the temperature didn't change. So since the temperature didn't change, the final energy state didn't change. So it's back where it was. What's the change in the final energy state of the gas?
0.
0. Okay? So calculate the amount of heat absorbed or released by the gas.
Q.
Q. And what is it equal to?
Is it 0?
I wrote it on this page.
First law of thermodynamics says delta E
Oh, so it's
int equals Q minus W.
so if it's 0,
You know that's 0.
so it's like the C.
Q equals W, so
5.76.
it's 5.76 times 10 to the fourth.
So since for an isothermal process Q equals W, you know that the amount of heat. Now, was it absorbed or released?
It is.
Q positive or negative? If the system if the system absorbs, Q is positive. So it's absorbed.
In order to expand its volume.
Yeah, in order to expand its volume and do work. Okay, now let's do the same thing for an isobaric process and see how these will change. So this is a different thermal process. So we got a sample of, I think I can probably do this and get done.